And we are live. Okay, so this is a calculator problem. So we have our calculators at the ready in radian mode. Always in radian mode, right? Okay. All right. So FRQ number 1 from 2016's exam. So water is pumped into a tank at a rate modeled by W at T is equal to 2,000 E to the negative T squared over 20 liters per hour on the closed interval 0 to 8, where T is measured in hours. Water is removed from the tank at a rate modeled by R at T liters per hour, where R is differentiable and decreasing on that closed interval. Selected values of R at T are shown in the table above. At time T equals 0, there are 50,000 liters of water in the tank. So we're asked to do 4 things. Part A, estimate R prime at 2, show the work that leads to your answer, indicate units of measure. Part B, use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or an underestimate of the total amount of water removed? Give a reason for your answer. Part C, use your answer from Part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. And Part D, for the closed interval 0 to 8, is there a time T when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Okay. As I kind of dive into this problem, I want to kind of maybe just highlight some things. My function W at T is giving me the rate that water is pumped into the tank. So I'm just going to say pumped in. So the rate that water is pumped in is given by W at T. Water is removed from the tank at a rate modeled by R at T. So R at T, which is given in the table, okay, I don't have an equation for R at T, I just have data points. That is going to be the rate water is pumped out. Okay? All right. They also tell me that R is differentiable and decreasing. So I'm just going to highlight that on our interval. Selected values of R at T are shown in the table above. And then at time T equals 0, there are 50,000 liters of water in the tank. So that's an important piece of information, an initial condition they kind of give us right there. Okay, so part A, estimate R prime at T. So R prime at T, the derivative of R, I'm going to use the information in the table, show the work that leads to your answer, indicate units of measurement. Okay, well, I hope this one is a confidence builder for you. So R prime at T, I'm looking in the table, I notice there is no T value for 2, so I'm going to use the 2 data points closest to 2, time 1 and time 3, and then it's basically just average rate of change. So it's going to be 950 minus 1190 over, because I started with the 950, my denominator is going to be 3 minus 1. Stopping right there, that's a numeric answer. Now, there's my estimate. There's the work that leads to my answer. Now all I have to do is indicate units of measure. So the units for my numerator are liters per hour. And then my units for time are hours. So I can leave it just like that. Liters per hour, or liters per hour squared. Okay? Bada boom, off to the races. Part B, use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. And then they ask, is it an overestimate or an underestimate of the total amount? Give a reason. Okay. Part B, a left Riemann sum to estimate the total amount of water removed from the tank. So in essence, I'm estimating using my left Riemann sum the integral of R at t. So again, I'm going back to my table. If it's a left Riemann sum, what I always do is I'm going to circle my y values, and if it's a left Riemann, I'm going to use the first one, second, third, and fourth, and I'm not going to use that last one. Now what I need to have is my change in t, 0 to 1, that's 1. From 1 to 3, that's 2. 3 to 6 is 3. 6 to 8 is 2. Yeah, Gabriel? You got it. I'd cross out that 1340, and I'd circle the 4 successive ones. You got it. That just keeps me from like using the wrong y values. Okay. Now I'm just going to pull them together. So it's 1 times 1340. 1 times 1340 plus 2 times 1190. Guys, if you see me do something wrong, holler out. Plus 3 times 950. And then my last one, 2 times 740. Okay. So there's my left Riemann sum. They don't ask me to indicate the units, but that's going to be, if it's estimating the total amount of water removed, that's going to be in liters. Okay. Is this an overestimate or an underestimate of the total amount of water removed? Okay, I just did a left Riemann sum. They told me in the stem of the problem that R is decreasing. So I'm going to just to make sure I don't kind of mess this up, I'm just going to draw R as a decreasing function. Doesn't matter if I draw it decreasing concave up, decreasing concave down. And then if I do a left Riemann sum, I can see that this portion right here is an overestimate. Even if I'm doing it like this, it's still an overestimate. So I'm going to answer their question and say, this is an overestimate. The left Riemann sum is an overestimate. Now I have to justify my answer, give a reason for your answer, because R at t is decreasing. Okay. All right, all right. Part B in the books. Part C, use your answer from Part B, okay, to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so for Part C, I can think of the amount of water that is going to be in the tank at the end of the 8 hours is really going to be made up of 3 different things. So this is Part C. So it's going to be the amount of water at time 0, which is given in the problem as how many liters? 50,000 liters right there. Guys, I can tell you right there, that's going to be a commonly kind of forgotten piece to this. People are leaving off the 50,000. It's going to be plus the amount of water that was pumped in from time t equals 0 to t equals 8. So to get that portion, I need to look at what function is giving me the rate pumped in. Okay, that's the W at t right here. So in order to get the amount of water pumped in, I need the integral of W at t. And that's going to be from time 0 to time 8. Okay. So that definite integral right there will give me the total amount of water that was pumped into the tank from time 0 to time 8. Okay. And then the last component of this is going to be minus the amount of water that was pumped out on that same interval. from t equals 0 to t equals 8. Okay? That is what we did in part B. Okay? So this is going to be from part B. So I'm just going to kind of, since I'm in Notability here, just kind of highlight what I just did there. And that's what I had from part B. Okay? Now, I need to make sure that I'm going to subtract that. So I'm going to put a subtraction sign, and I'm going to put brackets around that. Okay? So I've got my 50,000. Now, can't leave my answer like that. I have to evaluate this. And this is where I'm going to use my calculator. Okay? So in my calculator, I'm going to set up, I'm going to go Math 9. Brings up my definite integral template, lower bound of 0, upper bound of 8. And then what I need to put in for my integrand is W at t. So that's 2,000 times e. I don't need to put the multiplication. I can just put e to the x. And then it's e to the negative. I'm obviously using x squared in my calculator for t. X squared, and then divided by 20. dx. Say a short prayer, hit enter. Hope I have a correct answer. You got it. Let me, just going to take a picture. Yep. You good? Okay. So that's what I've got in my calculator, that definite integral. Okay. From 0 to 8 of 2,000 e to the negative x squared over 20 dx. And that's my answer. Now, the problem said to enter this, our answer for this part to the nearest like whole number. And so what I can do is I can just take 7,836 for my number right here. Okay. So that's what I'm going to do on that. So that's 7,836, the 50,000 added to that, minus that hot mess right there. I'm not just going to rewrite it, but it's just going to be that. Okay. That's a numeric answer. I'm good. I could throw some units on that. That's going to be liters. Okay. All right. All right. That's part C. Okay, part D, for the closed interval 0 to 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Okay, so for this one, I need to remember W at t and R at t. Okay, R at t is the rate removed, and W at t is the rate added. And they're asking, is there on our interval from 0 to 8, is there a time where the rates are equal to each other? Yeah, Max? I did. I'm guessing this last part. Yep. So it's the 50,000 plus the amount that's pumped in given by that definite integral minus the numeric answer I got for part B. You got it. Okay. So part D, one way I could look at this is I could say, okay, W at 0, which I can use my calculator to find, or actually I could even just look at it and say, if I look at this function, W at 0, that would be e to the 0, which is just 1. So W at 0 is 2,000. Okay. R at 0 from the table is 1,340. Okay, and then W at 8 and R at 8. R at 8, I can grab from the table. That's what I crossed out right here. That's the 700. And W at 8, I can use my calculator to find. So I'm just going to pull in Y1, and I want W at 8. Nope, I lied. I haven't put that in as Y1, so I can just plug that in. So it's 2,000 times E raised to the negative. And here's where I'm going to plug in. I'm plugging in 8 for my variable there. So 8 squared divided by 20. And I get a value of 81.5244. You guys can double check me on that, make sure I'm coming up with the right answer on that. Okay. Okay, so let's look at what we've got here. We're basically saying when time is 0, we can say that W at 0 is greater than R at 0. So what? The rate that the water is being added at time 0 is greater than the rate that the water is being pumped out. But at time 8, W at 8 is less than R at 8. Okay. So it switches at the end of those 8 hours. And now what? The rate that the water is being removed is larger than the rate that the water is being added. Okay. Now, I got to say one more important thing about this. And I have to say, because of what I'm just showing here, and because what? W at T and R at T are continuous. Then there is a T equal to C, where W at C is equal to R at C. Okay? Yeah, Matthew? And? Yep, no worries. Thanks for asking. Yeah, Luke?
So we're saying there is a point at which the time, or at which existing raised water is being removed and added, like because the two functions intersect.
You got it, because we're kind of saying, hey, if I draw like, let's say this is R at T, and this is W at T, it's because we're seeing this. At time 0, and at time equals 8. Okay, that's basically what we're seeing. And because they're both continuous functions, there's gotta be some point where they're going to intersect, and so they're equal to each other. Okay? All right. Okay. Moving ahead with vigor. Question 2, particle moves along the x-axis. The velocity of the particle at time t is given by v at t is equal to that equation. The particle is at position x equals 2 at time t equals 4. Okay? So I'm going to just highlight some info. Obviously, this is our velocity function right here. And they also tell us the position of a particle at a particular time. So our particle is at x equals 2 at time 4. So maybe to wrap our brains around this problem, we can just think of, we've got the x-axis. And we're saying at x equals positive 2, our particle is located there at time 4. So whatever, 4 seconds, 4 minutes, 4 hours, whatever, after we say go, that's where our particle is located. and our particle is just moving back and forth along the x-axis. Okay? Okay. Well, what I'm going to do to save maybe some time, again, still a calculator problem, I'm going to take this function, because I've got kind of an inkling that I'm going to use this function multiple times in my calculator. So I'm going to put it in my calculator as y1. So I'm going to my calculator, and under y1, I'm just going to input this function. 1 plus 2 times sine of x squared for the t divided by 2. Close parentheses and enter. Okay, got a trig function there, right? I got sine, so I need to be aware, gotta be in radian mode. If I'm not in radian mode, I'm going to be in trouble. Okay, all right. So first question they ask, at time t equals 4, is the particle speeding up or slowing down? All right. So to answer this question, I need to look at v at 4, and I also need to look at v prime at 4, which is acceleration. Yeah, Gabriel? Yeah, I'm going to show you one way on the calculator I could do it, but you're exactly right. You could do it that way as well. So what I want to do first off is I want to just look, since I've entered velocity in y1, I want to look at the graph, and I have to make sure that my graph includes this t value of 4. So I'm just going to do a quick window setting. My x-min, going to set at 0, x-max is 5, and I'm going to see what I'm looking at. Okay, so there is my velocity function that I'm looking at. Each tick mark on the horizontal represents 1. So I've got that. I can see it 1, 2, 3, 4. I can see velocity is positive. So I'm just going to indicate that. Velocity is positive. Now I'm going to use my calculator to come up with the value for v prime, which is acceleration at that same time. So from my graph screen, I'm going to go second trace, and I want to select option 6, dy dx. And now what I want to do is I want to put an x value of 4. And there's my answer. And I can see acceleration at time 4 is what? Is a negative value. Okay, so that's all. I don't even really care about the magnitude. I just care about the sign. So now I can go back to this and say v prime at 4 is negative. Therefore, the particle is doing what? Signs are different. The particle is slowing down. Okay. I go to in my graph, I go second trace, and then it's option 6. And that'll give me the derivative at a particular point in my graphing window. Okay? Okay. So there's part A. Find all times t in the interval 0 to 3 when the particle changes direction. Justify your answer. Thank you, sir. May I have another? The particle is going to change direction when velocity changes sign. So what I want to do, I'm going to go to my graph, and what I want to do on my graph is make sure this time I'm looking just on the interval from 0 to 3. So I just want to make sure, so I'm going to change my window settings, and I'm going to change my x max to 3. Okay, now I'm just looking at the interval from 0 to 3, and I can see right there velocity only crosses the t-axis one time. So I'm going to use my calculator to find that. I'm looking now for a 0, that's option 2. My left bound, that looks good. Right bound, I need to move to the other side of my 0. enter, guess, and there's my answer. 2.7074. So at time 2.7074, that's one of the times where the particle changes direction. And my justification is because via t changes from positive to negative at that time. Okay? Bada boom, that's my justification for part B. Okay. Part C, find the position of the particle at time 0. Okay, I'm asked for the position of the particle at time 0. I'm given velocity. So to get from velocity to position, what do I got to do? Do I have to integrate or do I have to differentiate? I got to integrate. Okay? Yeah, Gabriel? Four truncated. 4 truncated. Don't worry about rounding. Just read 4 decimal places off your calculator and move on to the next one. Really good question. Okay? Okay. So for the position of the particle at time 0, I'm going to set up an integral and I'm going to set up a definite integral. I know it's going to be the integral of velocity, dt. And now the question is, what am I going to use for times for my lower and upper bound? 0 and 4. Okay? So I'm going to set it up. 0 is my lower bound. 4 is my upper bound. That tells me that according to FTC part 1, the antiderivative of velocity would be position, which we might use for x here. And it's going to be x at my upper bound minus x at my lower bound. So this is the position at time 4. And this is the position at time 0. Okay? I'm asked to find this, the position at time 0. And so what I want to do is I'm going to rearrange this. So I've got x at 0 is equal to x at 4, the position at time 4, minus the definite integral from 0 to 4 via t dt. They've given me x at 4 in the stem of the problem. The position at time 4 is 2 minus this definite integral, which I'm going to use my calculator to find for me. Okay? That's going to give me my position. So in my calculator, I want to put, and I want to enter 2 minus that definite integral. Okay? So I'm entering the entire right side in my calculator. So I want to do 2 minus the definite integral, math, right? Math, option 9 brings up the integral template. And now I'm going from 0. What was my upper bound? Upper bound was 4, right? Okay, and the integrand is stored in my calculator as what? Y1, okay? I can get a shortcut. If I do alpha trace, that brings up my Y variables. I select Y1, and then I go over dx. Say a short prayer, and there's my answer. Again, I want to take 4 places truncated, so I'm taking negative 3.8150. Negative 3.8150.
How did you make it the integral of y1?
Okay, I got y1. It's already stored in my y1, right? And so then, again, what I did here, I'll just do this again. I'm doing 2 minus, right? To bring the definite integral, it's math, option 9, that brings up the definite integral template.
Let's see, you did that first.
You got it. And then I'm just dropping in the numbers there. 0, lower bound, 4, upper bound. The Y1, you got it. The Y1 is already input. And so what I'm doing to get to the Y1 is alpha, trace, and that brings up my Y right there. Yeah, Cam? Great question. Great question. The reason why is the 4 comes from the stem of the problem where they gave me that initial condition. The position is at x equals 2 at time 4. And then in part C, they're asking me to find the position at time 0. So I got to use 0 and 4. Okay. I could have flipped them around and had 4 as the lower bound, 0 as the upper bound. Doesn't matter. But then I just need to carry that through FTC part 1. Sweet.
Did you have to do the 2 minus, or could you have just figured out the value of the integral and then just put that in, or that's it?
Well, no, you got to take 2 minus the value of that integral, because all that integral is basically giving you is the displacement that the particle moves from time 0 to time 4.
I mean, you don't have that, you could leave it at 2 minus whatever value you get.
Yes, as long as, again, you're 4 decimal places to the good. My question is, I mean, if it's a calculator problem all the way, just do 2 minus the definite integral. Okay. Part D, find the total distance the particle travels from time equals 0 to time equals 3. Total distance. So that's going to be a definite integral from 0 to 3. But now my integrand, what's my integrand going to be? This is key. I want total distance. The integrand's got to be what? Absolute value of velocity. So it's the absolute value of velocity dt. If I just take the definite integral of just velocity, that's going to give me the displacement from time 0 to time 3, not the total distance. Okay? Okay, so my calculator, I hope you guys are kind of practicing the calculator skills that I'm doing here as well. So I want to bring up the definite integral. Now I'm going from 0 to 3. Now for my integrand, I want to bring up the absolute value. A couple ways you can do that. One way, I go to the catalog, second 0 for the catalog, and it's the first function listed, ABS. So I bring up ABS. Now I want to bring in my Y1. So alpha trace. There's my Y1. So now that's the absolute value of my function. And then I move over dx, say a short prayer, churning, hunka hunka burning love. There we go. 5.3012. Heck yeah, baby. 5.3012. Okay. No units. That is my total distance that the particle traveled times 0 times 3. Here we go. All right. Putting up the calculator. First 2 were calculator. Now we're going no calc. We don't need no stinking calculator. Okay. Question 3. Figure above shows the graph of the piecewise linear function f. I always highlight that to make sure I remind myself I'm looking at f on the closed interval from -4 to 12. The function g is defined by g at x is equal to the definite integral from 2 to x, f at t, dt. Okay. Does g have a relative minimum, relative max, or neither at x equals 10? Justify your answer. What we got to do is get that link between f and g. So, and it's going to be right here. If we take the derivative of both sides of that equation, we're going to get g prime at x is going to be equal to, according to FTC part 2, it's going to be equal to f at x. So now we've got this link that the graph of f is also the graph of g prime. I need to write that somewhere on my exam paper so that I show the reader I've made that connection. If you don't do that, you're toast. Now I can look at this and say, does G have a relative min, relative max, or neither at x equals 10? Justify your answer. So now I'm looking at x equals 10. I see G prime is negative, goes to 0, it goes negative. Therefore, G has neither. I'm going to show you. G has neither a rel max or rel min at x equals 10 because G prime does not change signs. Yeah, I'm probably, since I'm talking about G, I'm more comfortable that I'm talking here referring to G prime. They're synonymous, but I'm just going to use G prime. Doesn't change signs. Okay? That's all I got for part A. Part B, does the graph of G have a point of inflection at x equals 4? Now we're looking at x equals 4. So we're looking right here on our graph, and they're asking us for a point of inflection on G. Well, I see that G prime at x equals 4 changes from increasing to decreasing. So that would be a point of inflection on G. So B is, yes, G has a poi. Can I use poi? Heck yeah. At x equals 4, because sometimes you feel like a nut, because G prime changes from increasing to decreasing. Okay? That's my justification. Part C, find the absolute minimum value and the absolute maximum value of G on that interval from -4 to 12. Justify your answers. As soon as I see the word absolute, I'm getting excited and I'm making a table. Bada boom, bada bing. My table is going to have, on the right side, it's the function I want the absolute max and min of. That's going to be G. So I'm going G over here, and I want max and min. Now I'm just looking over here. My independent variable is X. I immediately, if not sooner, plug in my endpoints, -4 and 12. Okay. Now I've also got to look at, I'm looking for an absolute min and an absolute max. So I need to consider critical points of G. Well, critical points of G are where G prime are what? 0 or undefined. So I'm looking right here. I got to look at -2. And I'm looking right here. I could look at 2 because technically that's a critical point, but I don't have a change of sign. So I'm going to exclude it. I'm going to look at 6, but I'm not going to look at 10. Does that make sense? So I'm working smarter, not harder. So -2 and 6. I got to consider those points. Now I got to figure out, how do I get those values? I'm taking my function G at X, and one by one, I'm plugging those in. So G at X is equal to the definite integral from 2 to X, f at t dt. So to find G at -4, that's from the definite integral from 2 to -4, f at t dt. So I'm going from 2 to -4. So I'm starting at 2 and I'm going to -4. So I'm integrating in that direction from right to left. So I need to know the area of that triangle and also the area of this triangle. Now I can help myself out and I can say, you know what? This triangle right here is the same as this triangle right here, and those two are going to cancel out. So now I really only need to worry about the area of this yellow triangle right there. It's got a base of 2, a height of 4, so the area is 1/2 the base times the height, which is going to be, looks like what? 4 units. But now the thing is, I'm integrating which direction? From right to left. So I'm going to treat that as what? -4. So when x is -4, g at -4 is -4. Okay? Next one, I'm going to 12. G at 12 is going to be the definite integral from 2 to 12, f of t dt. So now I'm looking here, I'm going from 2, I'm going to 12. I'm going to play the cancel game. This big triangle cancels with that big triangle. So really all I've got to do is I've got to find the area of this. I already know the area of those triangles because that was the same triangle as what I just did here. So the area is 4, right? Now, do I treat that as +4 or -4? Remember this time, I'm integrating from which direction? From 2 to 12, so I'm going left to right. That triangle has an area of 4. I'm also going to call it -4 because it's below the x-axis. So that's -4 also. Okay? Next one is -2. Okay? I'm not going to rewrite that. I'm just going to go from 2 to -2. So I'm going from 2 to -2. I'm going from left to right. I know those two triangles are 4 and 4. So it's 8. Do I treat it as +8 or -8? -8. Okay? And then 6, I'm going from 2 to 6. 2 to 6. So 2 to 6. Oops, almost went from -2 to 6. 2 to 6. Sorry about that. I'm just looking at this one. That one has an area of 8. Treat it as +8 or -8? +8. Okay, I'm done. I got to do an absolute max and absolute min. So I'm going to say, it looks like the absolute min is right there. Absolute min. And it looks like the absolute max is right below it. We good? The beauty is, that's my justification right in the table. Not writing a single word, moving on with my life. Talk to me, Gabriel.
So when it says absolute minimum value, it's talking about the y value. They said absolute minimum would be x.
No, if it would say, to get to the x value, they'd have to say, where is the absolute max located? Or what is the x value of the absolute max? But if they just say the absolute max value of the function, you want the y value. Great, great question. Okay. All right. Last one here, part D. Can we do it? For the closed interval, -4 to 12, find all intervals when g at x is negative. Okay. This one was a little salty. One way you could approach this is you could look at what we just did in part C, and you could kind of just plot some points. So this is my part D, and I'm looking, if I do my points in order, I'm basically going, I know my interval is what, from -4 to 12. Okay. And I know -4, my value of G is at -4. So I'm down here at -4. Okay. Next one over at -2, I'm at -8. So it went down, okay, definitely negative there. At 6, I'm at +8. So here at 6, I'm at +8. Okay. And then what? At 12, I'm back to -4. Okay. So I know I've got a couple intervals at least where it's negative and then it went positive. One thing I can do is I can look at, remember my function right here, g at x, lower bound at 2. What if my upper bound is 2? Where's it at? So at 2, what's the value of g at 2? 0. So this tells me from this interval right here, from -4 to 2, my function is going to be negative. I'm going to stop it. I'm going to pause it right there because I want to finish this one completely. We're close on that.